So in this video, I want to talk to you about the one sample Z test. I think it's the easiest test when you're first considering hypothesis testing. And what I want to do is just build some deep intuition by using simulation. We're going to simulate many sample means, and we're going to look at that distribution and how that fits in with the standard normal distribution that we're going to use to work out critical values and p-values. And so I've opened this notebook, Understanding the One Sample Z Test for Population Mean. So we're going to just use simulation to better understand or get some intuition behind hypothesis testing in this very simple case where we have a mean under a null hypothesis. So here's our imagined research question. It's just made up, so let's have a look at it. It has long been considered that the population mean of some continuous random variable x is 67 milligrams per deciliter, and the population standard deviation is 6 milligrams per deciliter, and we're going to let this random variable x be a representation of some given hormone level in a blood sample. So there is a claim that an additive to a county's water supply lowers this hormone level, which we're going to presume is not desirable. And then if proven, the additive is, is going to be removed. So to investigate this claim, researchers are going to randomly select 40 random subjects from this population, and they're going to test this claim at a 5% level of significance. So we have to state this level of significance before we even start the study. So we have this idea of hypothesis testing, this mechanism that we've put in place. We go step by step and we can test the veracity of some claim. And we do remember that these hypotheses are stated in terms, remember, always of parameters, not in terms of the sample means. So here we go, the null and alternative hypothesis. Let's start with the alternative hypothesis, tailed alternative hypothesis, which sticks us with this null hypothesis, saying, well, we don't believe your claim beforehand. We're just going to stick to this conservative approach. We're going to say that the population mean is 67. But because we said alternative is less than 67, the claim, sometimes you'll also see that notation in textbooks. Well, if it's not less than 67, it's got to be 67 or more. But we'll typically stick with this. The mu is 67, and the claim is then that it is less. So we have this population mean hormone level under the null hypothesis. So our mu sub 0 is exactly 67 milligrams per deciliter with a population standard deviation. As we can see there, sigma, that's 6 milligrams per deciliter. So we can very easily take a computer and we're going to say, well, if that were true, if these were the parameters, just generate 40 random observations for me, please. And that's exactly what I've done with the code there. I said, well, give me 40 random values from this distribution under the null hypothesis, and we see 40 random observations. But why would we stop there? This is a computer. It can do a lot of stuff in a fraction of a second, and that's exactly what I'm going to do now. I'm going to instruct the computer to create 40 observations from this distribution under the null hypothesis, as if the null hypothesis is true. Take 40 random values, calculate a mean, but repeat this process 100,000 times over, so that in the end I have 100,000 possible means. And by the central limit theorem, I'm guaranteed for that distribution to look like this. X bar is going to be distributed by or described by the normal distribution on a mean of 67, and then this variance, which is the square of the standard error, so 6 squared over 40. So remember, I'm going to deal with the standard error, so I'm going to square that. That's going to be 6 over the square root of 40. By the central limit theorem, we are going to see that these means are, have to be distributed like this. But let's have a look at it. Let's visualize it. I've got 100,000 means. Let's create a histogram of those 100,000 means. And I'm going to just overlay on top of that this normal distribution on a mean of 67 and a variance of 6 squared over 40. And look at that, that's exactly what we see. Now, I did not plot all 100,000 values. That's a bit of overkill, so I just randomly selected about 1,000 of these 100,000 to create my yellow histogram. And I've overlaid on top of that this normal distribution. And look at that, it's a fantastic fit. Okay, this is some visual. I mean, now I've only, plotting 1,000 of these, and even 100,000, is not really enough. You can imagine that I have to do this an infinite number of times. I will get to this theoretical distribution by the central limit theorem. But even here, with a small number of simulated means. Look how beautiful this is. So let's just investigate this. Remember this theoretical distribution under the central limit, using the central limit theorem at least, I should see a standard error of 6 divided by the square root of 40. And if I calculate 6 divided by the square root of 40, that's what I get, 0.948683. Now let me look at the standard deviation of my 100,000 simulated means and look at that, 0.95. 0.95, and if I sort of round that down, that will also be 0.95. Look how close that is. And 100,000 is a lot, but it's actually still very few. But look how close that is. It's really this visual representation and looking at the theoretical standard error and from the central limit theorem and looking at the standard deviation then of my sample means, my 100,000 sample means. Look how close these things are. And you can imagine if I increase that 100,000 number, I'm going to get closer and closer and closer. Those values are going to get closer to each other. So let's just start thinking about this idea of hypothesis testing. What are we trying to say here? The claim was that it's less than 67, the population mean. Now what we're going to suggest is that these researchers then go out and they select these 40 random subjects and they calculate a mean for those 40 values. And let's just imagine that they get a mean of a sample mean of, I've got it right there for you, 65.9. So I know, I've just seen a picture of what that distribution of means are going to be, and I have to think, where does this mean fall, compared to those 100,000 means, or then this distribution under the null hypothesis using the central limit theorem. So what we say is, well, we look at this idea of theirs, this claim of theirs was that it must be less than 67. So why don't we look at the proportion of all the 100,000 that were 65.9 or less? That is how we're going to express ourselves. We're going to look at 69.5 or more extreme. And by more extreme, we mean towards the lower tail because it was a one-tailed alternative hypothesis towards the lower tail. So that proportion of that 100,000 values that are at most 65.9. And I can do that very simply. And that's what I've done here with a code that we can see there. I said, calculate for me the proportion of those 100,000 values that are 65.9 or lower, or at most 65.9. And it comes back 12.31% of those values, of those 100,000 values, were at most. In actual fact, that is my p-value. That is the probability of a randomly selected mean being at most 65.9. And that is the procedure that we follow when we have this one-tailed alternative hypothesis towards the lower tail side. We just look at the proportion of all the values up until that value that we find for our one single study, and that was 65.9. And so let's just have a look at that. I've zoomed in on that for you. And I'm showing you both the central limit theorem, the theoretical distribution there from the central limit theorem. So we're going to see the normal distribution on a mean of 67 and then a standard deviation of 6 over the square root of 40. We see that, and we also see the part of that histogram, just trying to show to you that that is 12.5, or 12.31% of those 100,000 values were 65.9, or at least lower than 65.9. And another way to look at it then, though, is, well, all these values, all these x bar values, the 100,000 that I have, or then theoretically from negative infinity, positive infinity, let's take that level of significance of 5%. Let's look at this lower 5% of all those values. And that is going to be my region of rejection, that if I find an x bar in that region, I am willing to make a type 1 error, meaning I'm going to reject the null hypothesis and accept the alternative hypothesis. Why do we call it an error? We call it an error because all these x bar values are totally possible and true under the null hypothesis. That's the only distribution I can generate, is the one under the null hypothesis. So that's exactly what we're doing here. We're deciding that, okay, it falls in this region. It's totally legitimate to fall in that region, even if the null hypothesis is true, but I'm willing to make an error. And if we do this, we're only going to make an error 5% of the time. Think about that, because it is in this least probable area. So what can I do? Well, I can think about at least calculating some value of x bar, which below that value I'll find these 5% of values. And that's going to be my critical value. So how would I do that? Well, let me just use percentiles. Remember what a percentile is? If I have the 50th percentile, that's the median, or the second quartile, all the same thing, means 50% of the values are less than that value. So why don't I take my 100,000 means and I just look at the 5th percentile? That's the value for which 5% of the values will be less than. So I'm just thinking of putting them in ascending order, and I'm looking at this lower end. And look at that, I find a value of 65.435. That is my 5th percentile value. Just to double check on that, I'm saying in the code here, what proportion of those 100,000 would be less than 65.435, and it comes back exactly, 5%, because that's what we generated. So in the plot here, this is what we can think of our region of rejection. This is the least probable 5% of these values on the lower tail. So up until, of all my 100,000 values, everything that is less than 65.4, that'll only make up 5% of these values. And look at that, it coincides with this idea of this area under the curve here, the bottom 5%. And so through the simulation, we can start to understand what is happening with this hypothesis testing. We choose this 5% level of significance. That is our type 1 error rate. If we find an X bar in this lower 5%, we're going to say, well, let's reject the null hypothesis and accept the alternative hypothesis. If not, then we failed to reject the null hypothesis. And so let's summarize that all in this plot that you can see here. In the little red zone, you see there, I've written, it might be a little bit small, but it says rejection. That's our region of rejection. That is the least, the 5% least probable values on the lower tail. And you can see how a p-value and this idea of a critical value, you can see that these are sort of the same thing that we're doing here. So by this little red point, remember that was 65.4, that was our 5th percentile. If I look at the area under the curve, or the proportion of all cases that are less than 65.4, that makes up 5% of all these cases. But we found a value of 65.9. So if I look from there towards the lower tail, that'll make up 12% of all those 100,000 values, or theoretically here then 12% of this area under the curve. And that is larger than 5%. Okay, so you can clearly see from the summary of this graphic, the critical value approach and the p-value approach, they're exactly the same thing. So I'm hoping that this idea of simulating at least 100,000 values gives you a good understanding of how hypothesis testing works in this very simple case of the one sample z-test. Now, what do we usually do in a course in statistics? Well, we have this plug and play hypothesis testing, and I just want to go through it with you once again, just so you can see how well this fits in with the simulation that we've just done. So it's a 7-step process. Breaking it down, it just gives you a nice mind map to work. I always include a step 0 because I just want to summarize everything that I was told in the problem. I was told that the mean under the null hypothesis was 67. I was told that the population mean is 6. I was told that there are 40 subjects, and from this one single study, the mean turned out to be 65.9. So in step 1, I'm always thinking about what am I interested in here. I'm interested in population parameters. I'm not interested in statistics. I'm interested in population parameters. Someone else wants to read my study. They have got a different population in front of them. They want to know, can they use these results? So we need to know the population value. In step 1, we write that population parameter that we're interested in, and here it's the population mean hormone level mu. Step 2, we write our null and alternative hypothesis. We've seen that. In step 3, we write our level of significance. That is something we decide beforehand, the 5%. It's just something we decide on. Step 4, we're going to say what test we're going to use. We're going to use the one sample z-test, and that's why I like step 0, because if I see all those things summarized, it triggers my mind as to what test we're going to use. And so we say, well, X is a continuous random variable, sigma is known, and we have 30 or more subjects in our study, so this would be an appropriate test for us to use. Step 5, let's think about the test statistic. It's z. How is it distributed? Well, it's distributed by the normal distribution on a mean of 0 and a standard deviation or variance of 1, the standard normal distribution. And what we can actually say is under h sub 0. So important. That is how it's going to be distributed. Given that the null hypothesis is true, then this is what we're going to see. And to get to z, remember, that is just an expression of how different the sample mean is from the mean under the null hypothesis, expressed in units of standard error. So divide by sigma divided by square root of n. So we calculate that z value, or at least that's this probability, So if we write this down, as you can see in equation number 7, I've said let's write this down statistically. So what is this hypothesis testing? What are we trying to calculate? Well, it's a one-tailed alternative hypothesis on the lower tail. So we're going to say, what is the probability that the mean is less than 65.9? That is the sample mean that we found from our one study. Well, I'm going to keep that inequality. So what I do to the left-hand side, I do to the right-hand side. So first I subtract mu from both sides, then I divide by sigma, then I divide by the square root of n. I recognize this left-hand side of the inequality to be z, so I just substitute z in there. And if I do this calculation on the right-hand side, it turns out to be negative 1.1595. So those two things, the probability that the mean is less than 65.9 and the probability that z is less than 1.1595, they mean exactly the same thing. Those are equivalent statements. Step 6, now I've got to calculate a critical value. Remember, that's my 5th percentile value. So, up until what value will I find 5% of the area under the curve? What that proportion of all the area under the curve of all possible outcomes that would be in that lower tail. And if I use software or calculator, you're going to get to negative 1.64485. Now, our z value was negative 1.1595. That is not more extreme than negative 1.64485. So we failed to reject the null hypothesis. I can also use a calculator to look at the area under the curve from negative infinity up till 65.9, and I find that is 12.3%. You can use a calculator. We use the NumWorks calculator in the course. You have just used software just to show you how easy that is. So the p-value is not smaller than the alpha value, and we failed to reject the null hypothesis. Okay, in step 7, we have the same conclusion as we had when we used that simulation. So we're going to conclude that there is not enough evidence in the data at the 5% level of significance to show that the population mean hormone level is less than 67. So we start then again with the claim. Okay, we don't have enough evidence at the 5% level of significance. We did not find an X bar that would be in that region of rejection. Okay, so the results cannot justify removing this additive from the drinking water.